Kia ora koutou. I'm just going to make a quick video to try and expand a bit on the melting and boiling points of molecules. So in the video that I did on it, I kind of showed the intermolecular forces between these nitrogen molecules. And then what I didn't do and what I should have done is gone back to here and just said that each one of these circles represents one of those circles there. So it's the for molecules, as the temperature increases, there is going to be more kinetic energy. So I'll just draw this here. Okay, so if we were to show the kinetic energy or the temperature increasing, so I've got this line showing that the kinetic energy or the temperature is increasing as we go from across here, so solid to liquid to gas. For molecules, this will happen quite early on. So for nitrogen, it happens at like, if this was negative, like if that was -1, I don't know what it is, might be -200 or something like that, 200 degrees. Then at about -170, -170, it goes from a solid to a liquid. So let's say that point is -200, that point is -170, where it goes from a solid to a liquid. Those bonds start to break, and then let's say -160, we can look up the values, but I just haven't got around to it. At about -160 degrees Celsius, the nitrogen molecules, so these molecules, the intermolecular bonds will break because these nitrogen molecules have too much kinetic energy. They're moving around too fast for this bond, which is quite weak to be able to hold it together. So then the molecule will turn to a gas. So that's the melting and boiling points of fuels. If we think of an ionic compound, which is a 3D lattice, and I'll just do a little 2D kind of view of it. So you've got positive, negative, negative, and these are all held together by ionic bonds. So these are ionic bonds. Get too lazy and then it doesn't make any sense. So those are ionic bonds which are really strong. So because they're really strong, they're going to take a lot of energy to break. So if I was to show this diagram again here, but for an ionic compound, it would be perhaps something like this. You'd have all of they'll be rigidly attached, so there'd be those bonds there, like that. That is solid, and then at a liquid state, all of the ions would just be flowing over each other. So you'd have cations and anions flowing over each other, and they would take up the whole space of the container. So that would be the liquid. And then at a gas, it would still be the same. You'd have to heat it up to very high temperatures to get an ionic compound into a gas state. So if I was to show that same line that we had over here, under here, so let's say we go from a solid to a liquid to a gas for an ionic compound, these bonds here are way stronger for ionic compounds than they are for molecules. So here, this is going to be solid until about, I think, like 700 degrees for sodium chloride. So it's not until you get to 700 degrees that these bonds start to weaken and the ions can roll over each other. And then I'm not actually sure, for example, if this was NaCl, I don't actually know what the boiling point of NaCl would be, but it would be really, really, really high. Let's say 1500. Why not? So so that's the difference between the melting and boiling points between ionic compounds and molecules. So molecules, the things holding those particles in place, are really weak intermolecular forces, whereas with ionic compounds, it's slightly different because you don't have those separate, discrete molecules as particles. For here, the particles are ions, and all of the ions are held together by those ionic bonds in a whole lattice. So it's, yeah, so to melt an ionic compound, you have to break the ionic bonds, which are really strong, and so you need a lot of kinetic energy. So 700 degrees until salt starts to melt, whereas here you don't require very much energy at all to break the bonds in between there. So for nitrogen, you start to break the bonds at a really low temperature. So that's why, for example, liquid nitrogen, if you've kind of come across the uses of that, I think they use that for like in the Olympics with the bobsleds and the sleighs and whatever. For the tracks there, to keep all the ice really cold, they have liquid nitrogen passing through it, and so to do that they have to cool nitrogen down to around 170 degrees, and then nitrogen will turn into a liquid, but it has to be super cold. So hopefully that helps. Yeah, I'll just share this with you, and yeah, just to add on to the other video I did. Thanks everyone.